Hello and welcome to this tutorial. Today I'm going to be describing the process for programming an FPGA in Cardus Lite 18.1. We're going to go through everything in the Cardus interface that you need to know, and we're going to go through writing the actual test bench as well as reading in values through the logic analyzer. So our final result is going to be something that looks like this, where we're going to go from the code that we write out to a logic analyzer showing, okay, this is the bit that I affected. We're going to do that using a couple different things. We're going to be doing a test bench, because it's always good to write your test bench first. We're going to write our performance module. We're going to validate that our design works using a simulator. And we are going to allocate pin assignments to the FPGA, program it, capture values, and then we will be done. So I've already completed these files, the writing of them, and just going to go over what's being said here. Alright, so no test bench. I was wrong about that. This particular module doesn't have a test bench, but that's alright. I'll make things easier. So this is just a clock counter. It goes through these different values. So the first thing we do is we declare our libraries, and then we go in here and say, okay, these are going to be our ports. This is how it's connected to the outside world. Important to notice the standard logic vector that comes out of standard logic unsigned and 1164, so make sure those are included. That's kind of your basic package. Then we describe the behavior of our system. So what we're doing now is we're declaring the internal signals that can be thought of as variables in the classic programming sense, because these are going to hold temporary values within the module for processing, but they're not like these values, because these are actual silicon and aluminum, whatever, contacts. There is a clock, there is a button, there are green LEDs. These are real external interfaces, whereas this is what we're fabricating. So we're defining our clock process here. This is just going to downsample a 50 megahertz clock down to 1 second. We're going to do that by counting half the number of cycles. So here we are at 25, let's see, integer range, yeah, 25 megahertz, and then increment it. So we're doing 2 switches per duty cycle. So that'd be a 50%, not per duty cycle, per period. 2 switches per period, to make 1 switch every half period. Yes, 2 switches per period, in order to make that nice square wave that we see here. Alright, so once we've got that going, that's going to be running in the background, and it's going to be feeding values to this signal clock 1 hertz. and then we're going to go from clock 1 hertz, and we're going to use that to actually count up our LEDs. So this 000 da 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 da, that corresponds to actual chips that we're going to be, actual pins that we're going to be connecting to. So I'm going to pull up a picture of the board. Alright, so these 8 LEDs, okay, you can't see that. There are 8 LEDs here. Those correspond to the zeros in this vector. And so when we actually get into the pin planning and choosing pins that are going to connect to these, then we're going to find out, okay, this is where we want to go, this is what we want to do here. So that's kind of a visual. Alright, so now that we've got that going, ooh, that's hard to see. It sure is hard to see. Okay. So we've gone through our design. We're going to skip verification because we haven't written a test bench for this. I can do that hopefully the next time I spin up one of these videos. Find one that has a test bench associated with it. And then now we need to get that loaded up and programmed to this FPGA. So we're going to do that by running through these pre-made steps that come with Cardis. So all you got to do is go over here. Oh, I was not clicking on the right thing. And you're going to run all these steps. And yeah, depending on how fast your machine is, they're going to go. And it really isn't going to take very long, just because this is a pretty simple design. And run this. Write the net list. Okay, so now what we're going to do is go into the pin planner window. Okay. Assignments, pin planner. I've actually already completed this design previously. Hold on. Okay, so what we're looking at here is a kind of inverted view of the bottom of the chip. The bottom of the system on chip device. So this is going to allow us to choose certain pins. Different pins have different assignments. You find that sort of information about like what's allocated to what through a couple of places. So what you got to think about is that this whole thing is not an FPGA. This thing here is not even an FPGA. I mean, it might be, but it's more than likely a system on chip with a little bit of fabric. So that's important because you have a couple of things you need to think about. So, you know, you're going from this out to these pins, and then, you know, how does this know that it's connected to that? So this has, you know, these pin pads here. You'd say, okay, I want to be on pin like E8. And then you gotta say, okay, well that's connected to a wire that runs from here to here. But then that wire is gonna have a board name, like LED or GPIO. These have GPIO. So it's gonna go E8, GPIO, and then we need to think about our channel that we're bringing the data in on, which is this channel 0 here. So there's a lot of names for the same thing. Alright, and the other place that you're going to go if you need information about what you're building. Nope, that's my syllabus. Yeah, this bad boy. Okay, so this is information that's specific to this chip. So, oh, I just messed that up. Okay, so this is the EP4C E22, EP4C E6. This might not be the right one to reference anyways. Go here. I'm gonna go in here, Control F, GPIO. And then you say, okay, like pin. So what I ended up doing, you know, because we're trying to say we're gonna have the pin be adjacent to this LED. So I had to figure out which pin that was. So that involved going into here, kind of rotating it in my head and finding out by looking at the board that this is GPIO 0, JP1, going through here. And then we say, okay, that must be GPIO, what did I end up choosing? GPIO 20. So we're claiming that it's this pin right here that we're getting our signal from when we do this code, which is gone because I closed it. It's here then. Must be in Cardis. Yes, this code. We wrote the code, we put green LEDs. We're looking right now at the 0th LED, the least significant bit. We're going here to our pin planner, and we're referencing our data sheet, and we are looking at our board, and we are saying, okay, this is GPIO 20, which is going to be connected to E8, and then E8 is here. So what you do is you go into your node name, you get that there, and then you go through and you say, okay, location, and you just type in your name, your pin name. Of course, the thing to remember is that this is specific. This Cardis software only does work on this thing, the actual FPGA. I think I might have been wrong about this. This might not be an SoC. Sometimes it's an SoC with an FPGA inside. This one's just an FPGA. Either way, the Cardis is just to manage and program this. So everything out here was built by a different company, and you know, they've got their own designs, and you really need to go to that manufacturer to figure out how to work on these things or get some of these specifics. Alright, so we've got our pins. We've already gone through our design. Now we're going to open up the board programmer, which is this little doohickey, this little rainbow thing. Do your hardware setup. These boards come with a built-in USB blaster, I suppose. It's not always the case. Sometimes you have to get a little debug dongle. Anyways, you just hit start. If you need to navigate to your file, you just go to your working directory, output files.soft. Now it's programmed. Now we can see what's happening. We can see the results. So we've got our logic analyzer. We're going to go ahead and we're going to have it do 10 kilohertz for 1 second. Now remember, we programmed something that counts every second, so we really need to watch it for longer than that to see a thing. 5 seconds. There we go. That is our oscillating pin. And once I get my webcam working, which I think I could probably do that right now. I'd like to show you what it looks like once this is all built. New webcam. Alright, well, webcam's not working. Anyways, that's how you do it. Pretty fun stuff.